Today we're going to be reviewing basic probability. You guys have already dealt with the more difficult probability with the different distributions, normal, binomial, and the probability distribution table. So we're going to go back, look at some of your most basic probability stuff as the review. And as we continue along, next week we'll review statistics, and then we'll see how you do with probability statistics. That is one topic altogether. To start with, this is, all this is a review. Venn diagrams was a part of probability, being able to identify and locate different regions, where to place particular numbers of certain regions, et cetera, okay? So let's review some of this notation. Let's see how much you remember, or you can look back at your notes, because you can always use your notes for your problems of the day. What does this symbol mean here, the upside down U? Intersection. What word is associated with intersection? Like besides intersection? And. Okay. So let's say, if you were looking for
Good morning, Highlanders.
So the upside down U stands for intersection. And so let's say, you're trying to find the probability between Xavier hitting the target and Aaron hitting the target. That would represent the intersection, okay? What does this apostrophe mean? In the sense of derivatives, it does mean prime. But in the sense of probability, it means what?
Complement?
It means the complement, okay? So that means the complement, okay? So that's everything. What is like a word that's used to represent complement? Kind of like how and is used to represent intersection, what would be used to represent complement? Besides. That's a good one.
Other?
That's a good one. Both of those words probably would not be used in the IB question. Or actually means something different.
Okay. The rest, the outline.
Okay. Let's try not. Okay. So what's the probability that they do not play baseball? That means you're looking for everybody outside of like the baseball circle. Okay, that's what the complement is. And the other symbol that we have in here is the right side up, U. What does that stand for? The union. And what word is associated with union?
Or.
This is the one that has the or. Okay. So you have what they mean. You have how they could be represented in an actual problem in words. And so here I want the problem of the day was about practicing the shading part. Okay. Like what part of the Venn diagram would represent this? Clearly, the bubble on my left is representative of A, and then the bubble on my right is representative of B. Now, in each one of these Venn diagrams, there's one more thing that's missing that you should always have when you yourself have to draw a Venn diagram.
Titles?
Well, I got my titles and my bubbles for A and B, but there's something else.
The outside part is not included. I forgot the name.
What is this box called? This rectangle. Look through our notes.
The complement? Well, is that like where you put like a C or something?
Like
anything that doesn't fall in there would go in the box.
Yeah, true. Technically, inside the box would be the complement of A and B, but what is that box called? Like the actual rectangle part, what is that actually called? It is a U. That represents the universal set. That means that whatever the universal set was, whether it was the set of numbers from 1 to 20, all of those numbers should be a part of that universal set. Without that U, your Venn diagram is not complete. And without that U, that Venn diagram would be wrong. So if that was a part A, of a probability problem, you would lose 3 or 4 points right there without that U. Okay, you have to make it complete. So every single Venn diagram should have a U, and of course your labels or your titles of your respective bubbles. Now let's go through and let's do some shading here. So I have the union between A and B. Not the union, I'm sorry, the intersection of A and B. Well, the intersection is technically this part that's on the inside between the overlap between A and B. That's what the intersection is. But when it says the complement of that, that means everything that is what? Not the intersection. So what you should have shaded was everything that was not that yellow shaded area, which should have been essentially the box minus that opening right there. Everything else should have been shaded, except for that opening. Questions there? All right, let's look at the next one. It says the union between A and B. The union means or. What would need to be shaded?
The circle is beside the intersection.
The circle is beside the intersection?
Yeah, without the intersection.
Why not the intersection?
Because it says or.
But the union actually means A or B or both. So it's actually everything, all the bubbles, including that intersection. So if the union is all of the bubble, including the intersection, then the next one that has the complement would be what?
It would be everything outside.
Everything outside. Everything outside the box. I'm not including the circles at all. The next one, A complement intersection B. So that means everything not in A, but that intersects with B. What will be shaded?
Oh, the box. And B for sure.
The box and B for sure?
But I don't know about the intersection between A and B.
Okay. On these, if you need to, break it up. What would represent not A? Like what would be shaded to represent not A?
Everything but A.
Everything but A. So I'm gonna do that in this light blue color. Everything not A. That's including the intersection because that's everything that's not in A. What about B? What would need to be shaded to represent B?
All of B.
All of B, including the intersection because that is B. That is a part of B. So now we have the intersection between the two. The intersection is what part of what's shaded?
Orange. The orange. Or yellow. Yeah, the B only.
The B only. Because intersection, you can even add in the word for intersection for the overlap between what's on the left and what's on the right. So it'll be this part that's just in B, the part that's just in B. Does everybody understand that before I erase all the extra?
Not really.
Okay. So intersection means the overlap. So when you see the intersection between A and B, that means you're looking for the overlap between those two circles, which is this part right here. So if you're doing everything that's not in A and B, you need the overlap between what's not in A, which I did in that greenish blue color, and B, which was the circle for B. So the overlap between the two was just B only. So it doesn't include the intersection because the intersection has A in it, and I cannot include A. It wouldn't include the universal set because the universal set doesn't overlap with B. Now that's different from when you look at the union. Union means or. Another word that you can even add in with union is all. Okay? So union, it's A, it's not B, and it's all of that. Everything that's in A, everything that's not in B, all of it.
So
Go ahead.
A only and then universal.
A only and then the universal. Yes. A only and the universal. For those who can't see that, here's A. Here's everything that's not in B. And it's the union. So that means everything that is shaded. So it actually would include the intersection as well. So it will be all of this, just not B.
I don't understand like why we're including the universal set in this one, but in the second one, we did.
Because it's the overlap between these two regions. So B and where A complement overlap did not include the universal set.
I mean like the one with the green.
The one with the green? Oh, because that is everything that's in A and everything that's in B. So just those circles alone. That's why we didn't include the universal set. And then the last one, you're looking between the universal, not a universal, the union between A and B. Take away the intersection of A and B. So what will be shaded?
Just A and just B.
Just A and just B. Because the union is all of A and B. The intersection is what's in between, but I'm going to take out that intersection because it says subtract. So then it's just A and just B. Questions? So we're going to be reviewing probability. I'm going to refresh your memory of how to find probability, the different formats that we did last year when it came to probability. If you can have your notes out and just kind of remember and highlight certain things, it's going to start flooding back because you guys do probability probably at least one time a day, right? Anytime you say the likelihood that I'm going to run this red light or do my homework on time or anything like that, you are performing probability. Okay, and so what probability is your number of outcomes in a particular event over the total number of outcomes, right? I shoot 100 free throws in a season of playing basketball. I make 65 of those free throws. So that means the probability of me making a free throw is 65 over 100. I'm a 65% free throw shooter. It's your number of outcomes divided by, your number of outcomes in a particular event or particular experiment over the total number of outcomes. Expected value, this should be very fresh in your mind as we just did it with random or probability distribution, binomial distribution, normal distribution. It's your probability of success times your number of trials. Again, if I'm a 65% free throw shooter and I shoot 100 free throws, then I'm expected to make 65. We're taking out any of the other elements of me being sick, me breaking my arm. We're talking about just strictly running off of the numbers. Complementary events. We talked about that with the Venn diagrams, but if you have complementary events, one of these things need to be true, okay? Complementary events and their original event must add up to be 1. So the probability of A happening plus the probability of its complement should always add up to equal 1. Because again, probability is always in between 0 and 1. For a pair of complementary events, if one event is A, then the other one is a complement or not A. So again, in my universal set, if I have all the students that play archery, then out here in the universal set will represent all the students who do not play archery. You can always find the probability of an event happening by doing 1 minus the probability of the event not happening. Meteorologists say all the time there's a 20% chance of rain. So then that means the probability that it won't rain is going to be what? 80%. Okay? So the probability that it will 20% or 0.20. So the probability that it will not rain, 80%. Together, they have to add up to equal 1. Sample space diagrams. Talked about this on Tuesday when we were going over your binomial distribution homework. Sample spaces are ways to represent all the different outcomes, okay? You can have a combination table. They could give you the information like so, where you have someone flipping a coin and someone rolling a die. Here represents all of your different outcomes. Head in 1, head in 2, tails in 4, so on and so forth. You also have this type of sample space, a grid. Throwing 2 die. There are no numbers associated with it, but if you look at this point right here, that basically represents rolling a 1 on your first die and a 1 on your second die. This point right here will represent rolling a 4 on your first die and a 3 on your second die. Usually these axes are labeled, so then you'll know which one represents your first die, which one represents your second die. A tree diagram. That was another way that we represented information. Okay, this one we used a lot. Like if you look at the 2 that we used the most, Venn diagrams and tree diagrams were the ones that were used a lot, that are still used a lot. So this tree diagram is very helpful in depicting combined events, okay? Such as rolling a die twice and looking at all the different outcomes, rolling 1 die twice, right? I can either get a 6 or I cannot get a 6. If I roll again, I can get a 6 or I cannot get a 6. No matter what, your branches, this probability and this probability should always what? They should always add to equal 1. No matter what part of the branch that you're on, it should always, I think I accidentally cut this part off. Yeah, there it is. No matter what, it should always add up to equal what? 1. Should always add up to equal 1. When two or more events happen at the same time or one after the other, that's usually when we use a tree diagram. It shows all of our possible outcomes. Okay, you go along the branches. Anytime you go along the branches, like if I take this probability and then this probability, what do I do to those two? You multiply them together. But let's say I wanted, oh, Jesus. I wanted the probability of getting a 6 on my second roll. That can happen by getting a 6 the first time and getting a 6 the second time, or not getting a 6 the first time, but getting a 6 the second time. What do I do to those two probabilities?
You have to multiply, like once you get to the 6 on the first one,
Mm-hmm.
and then the second one, you have to multiply those.
Mm-hmm.
And then after you multiply both of the branches, you have to add them together.
Exactly. You take those two results and you add them together to get the probability of getting a 6 on your second roll. Trying to refresh your memory on how we use tree diagrams. What is the probability of getting a 6? If you roll it. 1 out of 6. What about when you rolled it the second time? 1 out of 6. Those are called what type of events? Where one has no effect on the other? Independent. What's 1 6 times 1 6? What about not getting a 6? What's the probability of not getting a 6?
5 out of 6.
And then getting a 6?
1 out of 6.
So I multiply those two together. What does that become?
5 over 36.
So then you add them together and the probability of getting a 6 on your second roll would be 6 out of 36 or 1 6. Okay, as you can see, the branches, these added up to equal 1. Okay, and so that last note was saying just that. To find the probability of an event is made up of several different outcomes. You add together, or the probability of the different outcomes, assuming there's no overlap between them. If there is overlap, then you need to take that into account. Replacement, without replacement, with replacement, you have to take that into account as well with the tree diagrams. You can also have a frequency table. This is where probability and stats started to overlap because they are in the same topic. So you also want to make sure that you're able to work with these simple frequency distribution tables, okay? Just to refresh your memory. If this right here represents the days of the week and the number of students who are late, how convenient. How many late students were there for the week? How would I find it?
Oh, you add them 5.
You add them up. What'd you say?
85.
85? Trust me. So that would be our denominator. That would represent my total number of late students. So what if I will ask you, what's the probability that a student is late on Thursday?
7 out of 85.
7 out of 85, that would represent late on Thursday. Simple like that. Okay. What if I said, you know how we run take this week, right? How our school does it, we did odd on Monday, we did even Tuesday, even Wednesday, even today. What's Friday? What's the probability that the student's going to be late on an odd day?
53 over 85.
Very good, because I add the two on Monday and Friday, and I divide it by the total number of students who are late overall for the week. Very good. You can also have a two-way frequency table. Remember, with statistics, which we'll go back over, they can get more extensive. They have your totals for your number of males and females, along with your totals for the different age groups and your overall total in a two-way frequency table. And then last but not least, of course, you got your Venn diagrams. We use this one just as much probably that we use a tree diagram. This example says, find the probability that a number below 20 is an even squared number. Now, before you can answer this question, there's actually an error on this picture. Okay? There's an error on this picture. I want you to find that error. There's actually two errors. I want you to find both errors.
Okay.
Yes, we have the 6. The 6 is in the wrong spot. It should be in the even Venn diagram. Should it be in the even or the intersection? Just the even, okay? Then there's one more error. The issue y'all had during the problem of the day. I had to wait like 5 minutes for you guys to remember.
There's no universal label on it?
There's no universal label. Very good. Okay, so now that this Venn diagram has been corrected by moving the 6 in, including the U for the universal set, what is the probability that a number below 20 is an even square number?
Two out of 20 or 1 out of 10?
Exactly. There's 2 even squared numbers. There's 20 overall, and we reduce that to 1 over 10. Very good. What about the one at the top? Let's answer that question. It says, find the probability of adults of a certain age group staying in a hotel being, oh, that's in general, being male or female. Let's say this. Find the probability.
You're recording, right?
Yeah. Find the probability that you select a person at random from this hotel stay that is female or in the age group 18 to 25. I want you to find the probability from this example at the top that a person selected at random is female or in the age group 18 to 25. All right, what'd you get?
35 over 76 after you reduce it, maybe?
35 over 76 after you reduce? Okay, I got 35 over 76. What'd you get?
64 over 152.
What's that reduced?
I don't know, but I'm calculating it wrong.
You don't need a calculator to reduce this. What's the number that goes into 64 and 152? Don't you dare. They're both even. What's the number that can go with 2? Okay, so what's 64 divided by 2?
32.
And then what's 152 divided by 2? What's
76,
76? Keep reducing.
16, and 30. No, it's not that. 37.
16. What's 2 divided by 16?
Huh?
What's 16 divided by 2?
8.
Keep reducing.
8 and 8. 19.
Okay, so we got 35 over 76, and we got 8 over 19. Anybody get anything different? Anybody get one of these two?
I got it.
Okay. How many females do you have online? How many females do you have? Actually, and somebody other than Michaela and Julia. How many females do you have?
49.
You got 49 females, okay? Says it right here, you got 49 females once it adds up. How many people do you have between the age of 18 and 25?
21.
You got 21 right here. There's a problem if you add up those two numbers, what are you doing? Like you add 49 and 21, you're doing something that you shouldn't do.
You're counting the females that are 18 and 25 twice.
So what do I need to do with that 6?
You subtract it from the total that you get from the 49.
Exactly. So when you add those up and subtract from 6, you do get 64 out of 152, and it reduces to 8/19. 8/19. That concept of where you have to take out to the intersection between two groups is known as combined events, that or. The probability of A or B, or A union B, is the probability of A, female, plus the probability of B, 18 to 25, minus the intersection, females who are in the age of 18 to 25. Then you have your AND events. You got ones for independent events and mutually exclusive. Both of these, actually all 3 of these, are in your reference booklet. You just have to know how to use them. Independent events means that the outcome of one has no effect on the outcome of the other, such as the rolling of the die twice. Those are independent events. Mutually exclusive, that's when the intersections equal to 0. That means they have nothing in common. The example I gave you guys last year was when you look at a deck of cards and you pick a card, there's no way that you can get a card that's an ace and a king at the same time. There's no way you can pick a card that's an ace and a king at the same time. So those are mutually exclusive events. Speaking of cards, because some of these things you guys need to know about, how many cards are in a deck?
54.
Not
52.
54, 52. Don't include jokers. There's 52 cards in a deck. How many suits are in a deck?
4.
13. Oh, sorry.
Well, there's 13 cards in each suit. Each suit, that's a diamonds, clubs, hearts, and spades. How many face cards are in each suit?
3.
You got your jack, your king, and your queen. Ace is not considered a face card for those who play cards on a regular basis, okay? These are some things that you need to know. Something else that you need to know, especially when it comes to probability. How many days are in January?
31.
31, the month we're in right now. There's 31 days in it. How many days are in February?
28.
They do not consider leap years in IB. Even though this year we got 29 days in February, we do not consider 29 days. It's only 365 days in a year in IB. How many days are in March?
31.
31. How many days are in April?
30.
May?
31.
June?
30.
How you not know January? Because you're killing it right now. July? 31. August?
They just interchange after that, so it's gonna be 30.
This one's 31.
I didn't know that.
It's the knuckle trick. Remember I showed y'all the knuckle trick? Every dip was something other. Every hill was 31. You can do the knuckle trick also to help you out. September, how many?
30.
October.
31.
Everybody should always get that right. Halloween. November
30.
and December. Everybody should always get this one right.
31.
31. The knuckle trick is what I was talking about with, you can do this as well. If you start on your far side, any hill is 31, any dip is something else. January, February, March, April, May, June, July. If you connect with your other hand, July and August both have hills, so that's why it goes 31, 31. September, October, November, December. My knuckles are low, but you get what I'm saying here. Last but not least, we have conditional probability.
I have a question.
Yep.
So How do we know when we're supposed to multiply probabilities by each other, and how do we know when we're supposed to add them together?
Anytime you're dealing with independent events, you know that you're going to be multiplying your two probabilities together. Anytime you have multiple events also, you need to kind of, that's when it's going to kind of vary depending on the situation. So like if you have a tree diagram and you're going along the branches, you always multiply along the branches. But if you take into account this branch, a completely different branch, and maybe another branch, you add those respective probabilities together. If you have two people and there's like two different outcomes of like, what's the probability that you pick two females in the stay? You multiply them together because those are independent events. Me picking the first female and me picking the second female, two different events that get multiplied together, independent events there. But like once it goes past, like once you start like getting more into like the problem specifics, that's when you have to determine, okay, am I dealing with independent events? If so, I'm multiplying them together, or am I dealing with completely different outcomes? In that case, I have to add them together.
Okay, thank you.
Conditional probability, very common. This formula is straight from your reference booklet. I highlighted the back part of the format. The vertical bar, don't forget, always means conditional probability. The part that follows the bar is always your condition. Some trigger words to let you know you're dealing with conditional probability is given or such that. Another common one is if, or even before the question, if it says a female is chosen at random, find the probability that she is between the age of 18 and 25. Just that one sentence alone lets you know that, okay, you're dealing with a condition. I'm only looking at the females out of the hotel stay. Out of those females in the hotel stay, how many were between the age of 18 and 25? That's another example of conditional probability. So again, the vertical bar means conditional probability.
And B is always going to be your denominator.
B is always your denominator, so I'm looking for my probability of female. And out of the females, I'm looking for the intersection between female and 18 to 25. If you're like, where am I getting this example from? From that two-way table, okay? There were 6 females that were in between the age of 18 and 25, and there were a total of 49 females altogether. So it'll be 6 out of 49. A group of tourists went on safari to a game reserve. The game warden wanted to know how many of the tourists saw leopards, cheetahs, or rhinos. The results are given as following. 5 of the tourists saw all 3, 7 saw leopard and rhinos, 1 saw cheetah and leopard, but not rhino, 4 saw leopard only, 3 saw cheetah only, 9 saw rhino only. Draw a Venn diagram to show this situation or show this information. Venn diagram. That means I need that box that has a what on the outside? Don't forget it. How many circles should I have on the inside? 3. Should they be intersecting with each other? Yes. The reason why they should be intersecting with each other is because we know that 5 tourists saw all 3. So that means that there's an intersection between all 3 of them. Leopard, cheetah, rhino. If the problem tells you how to label your bubbles like this one did with L, C, and R, please make sure that you do that. Otherwise, put the full name on the bubble. I don't want you guys to get any of these easy problems marked wrong because you decided to make leopard C because, or P because it has, I don't know, something random, okay? Let's fill this in with what we know. 5 saw all 3. So that means the intersection between all 3 should be 5, which is right here. 7 saw leopard and rhino. 1 saw cheetah and leopard, but not rhino. 4 saw leopard only. If this description doesn't say only, such as here, 7 saw leopard and rhino, that means leopard, rhino, and the intersection adds up to equal 7.
So 7 isn't, like, it wouldn't go in like the middle of the two, it includes like, would it go in the intersection too?
So, sorry, I meant it did say and, not or, so I kind of showed the wrong thing. Since it does say and, that means you're looking at the full intersection between leopard and rhino. So where is that? That's right here. So this whole part should be 7. But as you can see, 5 saw cheetah as well. So how many saw leopard and rhino only? 2. Did everybody catch that? Actually, I'm gonna say it again. If it does not say only, then that means we're talking about the entire intersection between leopard and rhino, which is what I highlighted in like this aqua looking color. So that entire section should be 7 between those 2. Since I already know that 5 saw all 3, that means that 2 saw only leopards and rhinos. 1 saw cheetah, leopard, but not rhino. So where am I gonna put that?
The top intersection between leopard and cheetah.
Exactly. Since it said, but not rhino, that means they weren't even including the 5 that went to go see all 3. Now I have 4 that saw leopard only. That one's pretty straightforward. That goes leopard only, cheetah only, rhino only. There were 25 tourists in the group, and every tourist saw at least one of the 3 types. So 25 tourists, they saw at least one. So there's nobody in the universal set. Nobody went to go see gorillas or something. So then how many tourists saw cheetah and rhino, but not leopard? In other words, this missing spot right there. How do I find that out?
You add all the ones you have, and then you subtract from the 5.
You add all the ones that you have, all the sections, and then you subtract that from 25. Because if 25 people saw at least one of them, then there's a certain amount that saw cheetah and rhino, but not leopard. What number is that?
That doesn't include any like overall?
Not these numbers, because 4 is just leopard. 1 is leopard, cheetah, not rhino. 3 is just cheetah. 5 is all 3. 2 is leopard and rhino, not cheetah. 9 is rhino only. So by adding each individual section, I'm not including any type of potential overlapping of sections. 1. So that X is a 1. Questions on creating the Venn diagram?
No, ma'am.
Then let's do some probability. I went ahead and pulled it over here. I know this is a 1. Calculate the probability that a tourist chosen at random from the group. How many people were in the group? 25. So out of the group of 25, how many saw leopard? 12 out of 25. The reason why it's 12 is because it said leopard. That means everything in that L circle, not leopard only, but leopard. Then it says how many saw only one of the 3 types of animal? Out of, because it's probability, so we want to make sure that we have the probability here. Only 1. So only leopard, only cheetah, only rhino. How many saw only leopard, given that he saw only one of the 3 types of animal? It will be 4 out of 16. Very good. Why is it 4 out of 16? Given that means conditional probability. The part that follows given is the condition. Well, I know that 16 out of 25 saw only one of the animals, only one type. So out of that 16, which came from the blue color circles, 4 out of them saw the leopard. So that does reduce down to 4/16, which reduces to what? Very good. Now this one here, the one that I've written right here, this actually uses the full formula of the probability of the intersection divided by the probability of the condition. But you can also just look at it and say like, well, there's 16 of them, 4 out of 16. That works too. If a tourist is chosen at random from the group that saw leopard, how many saw leopard? 12. So if the tourist chosen at random was from the group that saw leopard, this is conditional probability. I'm only looking at the 12 that saw leopard. Out of those 12, find the probability that he also saw cheetah. 6. Not 1, because it didn't say cheetah only, or the only other one they saw was cheetah. No, they said cheetah in total. So how many, what's the probability of that?
Have.
And there you go. This is probability.